Okay, so this video is about friction, and in this video we're going to look at what friction is. You're going to be able to look at the difference between the two main types of friction called static and kinetic friction, do some math calculations, and then be able to look at certain situations and determine which types of friction you are looking at and dealing with. So, if you imagine like when you push your hand across a desk, you can feel some force of friction opposing it. Friction always acts in the opposite direction of what something is moving. Okay. So, but there's two types of friction, and again, they both always oppose the direction that you're moving. Okay. And the first type of friction is called kinetic friction. Kinetic means motion, so that's friction in motion. So when two objects are in motion, or one object is in motion and rubbing against another one, that makes kinetic friction. Okay, it's like if your tires are going along the ground as you're driving, the friction between the tires and the road while it's moving is kinetic friction. The other type is called static friction. That keeps two objects in place. Like if you push on something and it won't move, your static friction is what's keeping it in place. The friction between the object and the ground that's keeping it in place. Okay, and the friction is equal in strength and opposite to the direction of the applied force. And static friction will grow until you hit a point where you've put more force in than the static friction, then you can cause it to move. Okay, so you might push harder. So like if we look at this, you start pushing something, but it doesn't move. Okay, static friction grows as you put more force into it. Like I said, until you exert enough force, where now instead of being static friction, now you're opposing kinetic friction. Okay, so again, it starts to move. Okay, once you hit that over the static friction limit, then it'll move and you'll be able to push it. Okay, friction depends on the materials. So, and you know this, I think, if you look at like different types of materials, you can slide things across easier. The easier they slide, the less friction that there is. Okay. And the normal force matters. So the harder you have to push against the object, the greater the force of friction that results. So heavier objects have a greater normal force, and you'll have to push them harder. And you should, I think that's kind of common knowledge for certain things. Heavier objects you have to push harder to make a move because they have greater static friction because of the normal force. Okay, so if you push a block at a constant velocity, the friction force must be equal and opposite to the force that you apply. Think back to the Newton's third law of motion and actually Newton's first law of motion as well. Okay, objects that are moving at a constant velocity have no net force acting on them, so the forces are equal. Okay, and if you use a spring scale, you can figure what they are. So like this, if you pull this along at where the force on this spring scale is constant, you can actually figure out the force you're applying, and because it's moving at a constant speed, you will know then the opposite force is the friction force acting in the opposite direction. Okay, and again, you can stack additional blocks on the blocks to increase the normal force and repeat the experiment, and you should hopefully think about that. If you think that you're going to have to exert more force, you're right. Okay, now this, if you look back at this experiment here, there comes a point where when you're pulling initially, you don't get it to move. You're kind of trying to overcome the static friction, and there comes a point when you move. And if we could look at a force versus time graph of this big part up here, this is where the object is not moving. Okay, this is your static friction, and notice that static friction increases over time because the harder you pull on something, the more the static friction is going to be until it hits a point. At this peak right up here, the object starts to move. It starts to move, and then the amount of force you need to apply decreases. So your kinetic friction is less than your static friction in a situation. Okay, The spike is needed just to get it to move, and then from the spike down, now it's moving. That's a kinetic force. Okay, so static friction builds, builds, builds. Kinetic friction is constant. Okay, so they say that your static friction is proportional to the amount of friction, the force that you apply to it until it gets to a point where it moves. Kinetic friction is pretty constant. Once it gets moving at a constant speed, your kinetic friction is constant. Okay, so if we take that kinetic friction force and compare it to the weight, the normal force, you get the graph over here. So the normal force, which a lot of times is the weight, okay, the normal force on different types of surfaces is going to have a different amount of kinetic force that you have to apply. On rough sandpaper, you have to apply a greater force to get it to move. Rough table, a little bit less. A really highly polished table where there's not much friction, you don't have to apply much kinetic friction force to make the object move. Okay. So the kinetic friction force keeps it in motion. The static friction keeps it in place. Okay. So you would expect it to be harder to pull the block along sandpaper than along a polished table. So it's going to be higher. The slope is going to be higher. The slope of this line is what's called, it's mu. This little u with the extra arm on it is called mu. That's the coefficient of friction. It's the ratio between the friction force and the normal force. So really it's the slope of kinetic friction and normal force. That ratio or that slope is your coefficient of friction. Okay. So that ratio relationship is your coefficient of friction. Okay, and here's the math. So if you think about it, the force of friction, the force of your kinetic friction when it moves, the force that you have to apply to overcome the friction or equal the friction to keep it going at a constant speed is equal to your coefficient of friction times your normal force. And remember, if we're talking about something on a flat surface, the normal force is the weight of the object. Okay, so if you rearrange this, mu is equal to F kinetic divided by the normal force. Okay, so the force kinetic is equal to the product of the coefficient of the kinetic friction and the normal force. So the bigger your normal force, the more kinetic friction force you have to apply. The bigger the coefficient of friction, the more force you have to apply. Okay, they are directly related to each other. Okay, now that big spike that we saw earlier is what we call the maximum static friction. You have to apply that just to get it to move. Okay, the static friction force acts in response to the force trying to cause an object to start moving. Okay, and if there's a force trying to cause a motion, the static friction will increase up to a maximum point called your maximum static friction. Okay, so we say that the F static is greater than or equal to the mu static times your normal force. Excuse me, less than. Sorry, is less than or equal to the product of the coefficient. So you're going to hit a point where it starts to move. So everything less than that is what I would say F static is less than or equal to this. The F static times your normal force is what we call your Fs max, or your static friction max. When it's equal to this, that's your maximum. Everything less than that, it's not going to move. Okay. So mu s is the coefficient of static friction, and like it says, mu coefficient of static friction times your normal force is the maximum static force that must be overcome before motion can begin. So when you have a normal force times your coefficient of static friction, the object is going to move. Okay. So, like it says, the equations for kinetic and static friction force involves only the magnitudes of the forces. The forces themselves are at right angles to each other. So the normal force and your force of friction are at 90 degree angles to each other. Here are some sample coefficient of frictions, and you notice the more rough surfaces have higher coefficients of friction. Okay, so now we're going to do a sample problem. So you push a 25 kilogram wooden box across a wooden floor at a constant speed of 1 meter per second. How much force do you exert on the block? Okay, so first of all, let's look at what we have. That's kind of our situation. You're exerting a force, so there's my force vector, and the friction vector goes in the opposite direction. Okay, so if we look at this, we're going at a constant speed, so we have no acceleration, so we have no net force, which means the force that we apply is balanced by the force of friction because it's moving at a constant speed. And the force of gravity pulling down is balanced out by the normal force going up. So because Fp and Ff are equal, we're going at a constant speed. Okay, so what do we know? We know our mass, we know our velocity, we know our acceleration, and we know our coefficient of friction. What we don't know is the force we apply. Okay. Okay, so here's what we know. We know the normal force is weight. We know that the weight force is mass times gravity. So we substitute it in, and our normal force is 245 newtons. So in the equation, our Fn is 245 newtons. So because there's no acceleration, that means that our push force and our normal force are equal. Okay. So our push force, our force applied, is the coefficient of kinetic friction times the weight of the object. So we have our coefficient of friction, we have the mass, and we're going to use, in here they're going to use 9.8 meters per second squared as the acceleration due to gravity. We have the mass already. Now we're going to figure out some more information. Okay. So we know the coefficient of friction, we know the mass, we know the acceleration due to gravity. We can figure out our force applied, which is 49 newtons. Okay. So our units are correct. It makes sense. Yep. And it's realistic. Yeah. Okay, that is the end of this video. Make sure you can go back and look over it and make sure you know how to do all the problems on the assessment below. If you have any questions, please either contact me or ask them on the end of the form below. Thank you very much. We'll see you in class.